Alright, these are some examples for conservation of angular momentum. We may have done a couple of these in class, so if you need to skip forward in the video to see what you need, go ahead and do that. But to summarize, if there's no net torque acting on a system, the angular momentum of that system will remain constant. So we're going to be using that throughout these examples. Okay, the first one, we have solid disk at rest. A force is applied for 2 seconds. What's the final angular speed of the disk? When I read this, what stands out to me is we're applying a force at a distance, so that's a torque for a certain amount of time. So I remember the equation, it's basically the impulse momentum theorem for rotation, and that would be the torque times time, that's the angular impulse, equals the change in momentum, which would be inertia times change in angular velocity. Okay, so for this one, for the torque, we remember torque is the perpendicular lever arm times the force. So for the torque, we've got the 0.1 as our lever arm. The force is 0.63. Okay, so all that is the torque. And then times the time, which is 2 seconds. So that will be our time. And that equals I. For this one, we're given the equation 1/2 mr squared. So we'll have 1/2. The mass of the disk is 0.5. The radius is 0.25 squared. So all that is our rotational inertia. And the change in omega, the change in angular velocity, we'll have our final minus our initial. Since it starts from rest, we just use 0 for the initial. So that's our change in angular velocity. We solve that for the final angular velocity, and we should get about 8.1 radians per second. Okay, moving on to the second one. Okay, we did this demo in class, student on the rotating stool, holding the book in each hand is the demo we did, and when they extend their arms, they slow down, bring their arms in, they speed up. There's no net torque acting on the person, so all this is just conservation of angular momentum. You extend your arms, you increase the rotational inertia, you're going to decrease the angular velocity. You bring your arms in, you're going to decrease the rotational inertia, so you increase the angular velocity. Alright, so anyway, we start out conservation of angular momentum. In this case, we have something rotating about an axis, so we're going to use the equation I omega, rotational inertia times the angular velocity. So we can say I omega initial equals I omega final. Okay, for the rotational inertia, we've got 3 things in this problem. We've got the student, which we're told is inertia of 1.5, and then we have one 3 kilogram mass, and then we have the other 3 kilogram mass. So for the masses, they are considered point masses, so we're going to use the mr squared equation. Alright, so for the initial, we've got the student 1.5 plus 3, and starting at 1 meter out, and then plus the other 3 kilogram mass, also at 1 meter. So that is the inertia, and then the initial angular velocity is 0.5 radians per second. Alright, that equals the final inertia, which will be 1.5, still have the student. The 3 kilogram mass now is at a radius of 0.25, and the other 3 kilogram mass also 0.25. And then we're looking for that final angular speed. So we solve this, and we do get 2 radians per second. Check our answer, that is greater than the 0.5, so we should be in good shape there, because when the student brings their arms in, we have a lower inertia, so it should have a greater angular velocity. Alright, number 3, we've got the skater going at 2 meters per second, grabs onto a pole, rotates around the pole. So draw a picture here. Here's the pole. We're looking from a top view down on this. Okay, here's the skater, 60 kilograms, and then moving with a velocity 2 meters per second. Okay. Again, the skater holds on the pole, no external net torque, so we know the initial angular momentum has to equal final angular momentum. Before the skater grabs onto the pole, it's just a mass moving in a straight line. Whenever you have that, we're going to use the equation RMV. Remember, that's got to be a perpendicular distance, so that'd be like from here to here. In this case, her arm is 0.8 meters long, so it's going to be 0.8 meters. After she grabs onto the pole, she's going to start rotating around the pole, so we're going to have I omega. All right, so the R here and the RMV, again, is 0.8. Mass is 60. Velocity is 2 meters per second. And then the final inertia, the skater's going to be treated as a point mass just going around in a circle. So that will be mr squared. So we've got the mass of the skater is 60, and then the distance 0.8. Okay, so that is I. And then times omega, which is what we're looking for. So we solve for this omega, the angular velocity, we should get 2.5 radians per second. Okay, so even though the skater is not moving in a circle before this event, we still say she has angular momentum about that point, given with this equation RMV. All right, moving on. Okay, again here, if we look at the whole thing as a system, there's no external net torque acting on the system. So I'm going to solve this one over here. So we're going to say initial angular momentum equals final angular momentum. All right, before this collision, we just have a mass moving in a straight line. So that's going to be the RMV. And then it's going to stick to that, and the whole thing is going to rotate. Now the mass is going to rotate on the outside circumference of that cylinder. So the whole thing, we're going to have I omega. All right, so for the left side of the equation, R in this case is going to be D. It's that perpendicular distance between the velocity and the axis of rotation. So I'm going to have D, and then the mass is just a lowercase m, and then the V is a V initial, we're told that. And then in the final, our rotational inertia, we've got the whole cylinder. Okay, the whole cylinder, so that's 1/2, and then a capital M, capital R squared. And then we have this little mass, the sticky clay, is going to go around that circumference. Now, its distance to this axis of rotation will be capital R. So its inertia will be little m times big R squared. It's no longer D, okay, because it will be rotating around that circumference. And then our final angular velocity omega, if we solve this for omega, we should get 2m VID over big M, big R squared plus 2 little m R squared. Okay, any form of that really. I mean, we could cancel those two, and then we'd have the mr squared would have another coefficient down there. So any correct form of that is going to be okay. Of course, the variables in the numerator can be moved around. All right, then finally this last one. Okay, again, no external torque acting on the system, so we're going to have initial angular momentum equals final angular momentum. The initial angular momentum, we have this bullet moving in a straight line, so that will be RMV. And then the final angular momentum, everything will be moving in a circular path around that pivot point, so I omega. All right, so for the bullet moving, the distance R in this case is going to be a lowercase l, and then we've got the mass of the bullet, which is given as m, and then the initial velocity of the bullet is v. Yeah, speed v right there. That's what I was looking for. And then that equals I omega. Okay, so we've got two things that are going to make up the rotational inertia. We've got the bullet is going to be moving in a circle, and this block of mass m moving in a circle. it says the rod of length L has negligible mass, so we don't need to worry about that. All right, so for the bullet, we're going to have little m times L squared, and then the block will have big M times L squared omega. Okay, we solve that for omega. We get LmV over mL squared plus little m L squared. We can reduce an L out of that and say the final angular speed will be mv over big ML plus little mL. And that's our answer. Okay, so again, no net torque acting on these, so angular momentum is conserved. If you have an object moving in a straight line, use RMV, about a point, as long as it's not going through that point. If you had an object going through that point, it would have no angular momentum. And then if you have something moving in a circular path, you'd use the I omega for that rotational inertia. Okay, that's it.